Welcome to module 9 lecture 4, and we will continue with fiber concrete, which we just introduced in the last lecture. Now, we will look into issues like how it behaves in tension, because that is understanding this behavior will allow us to understand the crack arrestation property, also pseudo ductility and various properties of concrete. Then it is advantageous to use fiber concrete in flexure. So, we will look into flexure, then we will look into types of fiber. But before I just go to the fundamental behavior of fiber concrete under tension, I would like to mention 2 points. That this concrete is not a recent development, in the sense the use of fiber is age old. Second thing, one must understand that fiber reinforcement is not a replacement for conventional reinforcement, steel reinforcement or rebar which you use. In case of such reinforced concrete, which is also a composite, the concrete as a material and steel reinforcement as another material, they act separately. They are not in the steel is not reinforcement is not so well distributed into the matrix of the concrete to enhance the properties of the matrix itself. So, it does not enhance the properties of the matrix itself, rather acts independently and enhance the properties of the section or construction. While this type of fiber reinforcement, even though I might add steel fiber, it actually enhances the properties of the matrix itself. So, obviously, we are talking in terms of supposing if it improves the tensile load carrying capacity a little bit, which it does not really, most of it does not, but flexural load carrying capacity it increases. But by using fiber, I cannot replace the conventional reinforcement. So, that should be very clear right in the beginning, because these fibers essentially improves the flexural load carrying capacity of the matrix itself. In other words, what we talked about earlier, modulus of rupture. So, it would improve that property. So, that must be understood. So, let us go back to what we looked in the last class right in the beginning. We said that let us take an element, small element of fiber concrete. So, I have got fiber where I apply the load along the direction of the fiber, right, and the fibers are all continuous. P is the load I am applying. Long aligned fibers under tension that we can look into. So, delta L let us say is the length, small element. Fiber and matrix will have the same strain, because we are assuming that there is no pull, there is a right kind of bond between the fiber and the matrix. Therefore, fiber and matrix have the same strain. Therefore, load P is the sum of load carried by fiber and matrix. Part of the load will be carried by the fiber, part will be carried by the matrix. Let us say V m is the volume fraction of the fiber, matrix, and it is equals to 1 minus V f, because volume fraction, if I look at it, total volume, let us say volume fraction I am calling of, total volume is V, a part of it is a fiber and a part of it is matrix, sum total again makes it V. Therefore, if I talk of fractional volume, sum total of the fractional volume is equals to 1. In other words, I can say B m plus V f equals to 1, all right, or if it was I was calling it volume of matrix plus volume of fiber is equals to total volume, and V m is equals to nothing but B met by V, and V f is equals to nothing but B fiber by V. So, they are fractions, and that is why 1 minus V f, 1 minus V f, right, 1 minus V f. So, V f is the volume fraction of the fiber. Now, I will just, since we will look into this, last class also we just mentioned, total force is P equals to P f plus P m, the load carried by the fiber and the load carried by the matrix, the force P is the load applied. So, matrix carries P m. Therefore, this is nothing but sigma stress in the matrix, composite stress into area of the composite, which is the sum total. So, P can be written as sigma A, and P f is equals to sigma f, the stress in the fiber, and A f is the area fraction of the fiber, and this portion is the matrix stress in the matrix, and this is the area of the matrix, So, I can write it like this: if the length of this element is delta L, let us say this length is delta L, just I am taking it as delta L. So, delta L sigma A, multiply everything by delta L, length is delta L. So, fiber length is delta L, matrix length is also delta L. So, I have delta L everywhere multiplied, therefore, I get A f delta L sigma A f delta L by V. So, that is the fiber volume divided by overall volume V, and thus matrix volume by overall volume B. Therefore, this follows that sigma composite stress in the composite can be written as the volume fraction of the matrix into stress in the matrix plus volume fraction of fiber into stress in the volume in the fiber itself, stress in the fiber itself. So, if I simply now go further a little bit more, if I simply now go a little bit more, this stress divided by strain is same everywhere, epsilon is equals to epsilon fiber is equals to epsilon matrix, and epsilon composite. So, everything is same, all in tension, because I have applied tension. So, epsilon is same. Now, divide this by epsilon, this also by epsilon, and this also by epsilon. So, stress by sigma m by epsilon m, which is equals to epsilon is the same, is nothing but E m. So, therefore, it follows that E composite is equals to V m E m plus V f E f under the condition when load is aligned along the direction of the fiber, load and fibers are all aligned, and this is how it is. All right. So, that is what we just looked into in the last class. Then this is your fibers, they are not aligned, they are all random, and if I apply now load in the same manner as I did earlier, then for short randomly oriented discrete fiber, that is what our fibers are in concrete. They are like this, short randomly oriented, and they are discrete. I can add two factors. What will happen? Because the length is no longer the full length. So, I must multiply the load carried by the fiber or the stress in the fiber by an length efficiency factor, which will be a fraction. And since they are oriented, only the only like if this is like this, a part of the fiber will be load will come like this. So, part of the fiber will be effective in carrying the load. So, therefore, I put it what is called orientation efficiency factor. So, orientation efficiency factor, therefore, load efficiency factor and orientation efficiency factor. Therefore, stress now will be orientation efficiency factor and length efficiency factor, orientation efficiency factor multiplied by sigma f V f. This sigma f has to be multiplied. Sigma m, there is no problem, it is same, but this part I have to multiply by all the fibers will not be effective. So, I multiply by an orientation efficiency factor and length efficiency factor to get the composite stress. Similarly, the modulus of elasticity now can be related to this. Modulus of elasticity will be also related to this, because this epsilon still the strain, divide everything by the same strain, and you will get by this same efficiency factor. We are assuming strain in the matrix and the fiber is still same. There is no slippage, they have perfect bond between the two. So, NL is called nu L is called length efficiency factor. It is half for L equals to LC, which is called critical length, and is equals to L divided by 2 ice LC for L less than LC, and 1 minus LC divided by 2L for L greater than LC. So, we must look at what is LC and how this new values are coming. So, that is what we will look into the next slide. Now, first of all, LC is the critical length, and this is required for development of failure stress of the fiber. This is required for development of failure stress of the fiber, because I have the fibers inside the matrix. So, when I apply a pull at the boundary, at the end of the fiber, at the end of the, because they are discrete, they are not continuous, they are discrete. So, if I have, this is my matrix, the fiber starts from here somewhere there inside. So, the stress here, it will be all matrix will be taking the stress, and at this point if I have a pull like this, at this point stress will be, some of the stress will be transferred to the fiber, and we assume a linear stress variation through the bond, it will be transferred through the bond. So, when I am trying to pull this, 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 this will also try to pull this material, and at this point here the matrix is alone taking the pull. As I go, where there are fibers. So, this is my fiber, so fiber will also experience that pull, because there is a bond, and through the bond some stress will be transferred to the fiber, and fiber stress will go on increasing, but it will go to a maximum value possibly sigma fu, which is the ultimate fiber stress, or ultimate strength of the fiber. And after that, on the other side also it will experience similar sort of situation. So, it is a kind of development, the length required for development of the full failure stress, ultimate stress in the fiber. So, that is what I am calling as LC, or it is just let us see, we are calling it as LC, we are calling it as LC. So, this diagram will show you, this is my LC. So, this is sigma fu. So, this stress will be sigma fu, this stress will be sigma fu, this stress is sigma fu. So, this stress is sigma fu, and this a situation could be there, my fiber length is less than this, less than LC. So, L is less than LC, in that case full stress will not develop, it will develop some less amount of stress, this will not be sigma fu, it is less than sigma fu, and in this case sigma fu will develop, and beyond that. So, L is greater than LC, sigma fu will develop, but after that fiber cannot carry any more load or any more stress, it would have failed. So, therefore, if if it is longer than that length, fiber would still carry sigma fu, and rest of the stress has to be carried by the matrix or whatever it is. So, this is, if L is greater than this is the scenario, L is greater than this, the stress is on this axis is stress. So, we can look at this algebra now. So, efficiency is a efficiency factor is, supposing it was continuous fiber, then the load that it would have been able to carry. So, it is the ratio of the actual stress that it is carrying, average stress the fiber is having, to the one if it was a continuous fiber. So, if it was a continuous fiber, the stress in the whole of the fiber would have been sigma fu. For continuous fiber, it would have been simply sigma fu. Continuous fiber, for continuous fiber, this continuous fiber, right, this stress would have been, stress would have been simply sigma fu. So, this would have been sigma, throughout it would have been sigma fu, but here this is not a continuous fiber, therefore, the stress is less. Now, how much is the average stress? It is sigma fu at this point, 0 there, and therefore, it will be, average will be somewhere here, which will be this triangle divided by the base. So, what is this triangle? Half sigma fu, half sigma fu into LC, half sigma fu into LC, half sigma fu divided by LC, all right, half sigma fu divided by LC divided by LC, that is the average. So, half sigma fu into LC, this divided by LC is the average stress, that is this value, and this divided by sigma fu, which would have been there throughout, it will give me the length efficiency factor. So, that is what I have done, that is what I have done. So, this expression shows this one. So, therefore, it gives you simply this will cancel out, this will cancel out, this will cancel out, this is equals to half. So, length efficiency factor is half for length efficiency factor is half for length efficiency factor is half for L equals to L C. So, that is what we just mentioned earlier in the previous slide. Length is half for L equals to L C, critical length, and it is if it is L divided by twice L C for L less than L C, and 1 minus L C divided by 2 L for L greater than L C. So, let us see for the second case. Second case, what will happen? 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 Let us see. In this case, the stress here is sigma f, which is less than sigma fu. How much less? The sigma f by sigma fu will be equals to L divided by L C. L divided, if it was half L C, then you would have got it, because if it was L C, if this was half L C, then the stress in this case it is smaller than this. So, actually this is L, let us say this is my L. So, the stress developed would have been sigma f here. So, sigma f by sigma fu will be simply L divided by L C. So, sigma f is equals to sigma fu into L divided by L C. Sigma fu, so this would be sigma f would have been. So, input. So, what will be the average stress here? Average stress here, average stress will be half sigma f into L, right, divided by L is the average stress multiplied by not multiplied, but sigma fu is what? Sigma fu is equals to half sigma fu into L divided by L C into L, right, and this divided by sigma fu gives me the length efficiency factor. So, this L will cancel out, sigma fu will cancel out, L will one of the sigma fu will cancel out sigma fu L by L C. So, it is there has to be some L somewhere, half sigma fu L, the average stress will be divided by this, and this divided by sigma fu simply, right, but sigma f is equals to sigma fu L divided by L C. So, there is another L anyway here. So, this one L will cancel out, but there will be sigma f when you replace, there is an L divided by L C. So, you get this as in this case you get the efficiency factor as L divided by L C, L divided by 2 L C, L divided by 2 L C, L divided by 2 L C. In the second case you get L divided by 2 L C. Just let us do it here right now, because sigma f is equals to sigma fu L by L C. Average stress is half sigma fu into L divided by L, average stress, and nu L will be equals to half sigma f, L by L will cancel out, divided by sigma fu, and half remains. Sigma f is nothing but sigma fu L by L C, and this divided by another sigma fu, because this sigma fu. So, this will cancel out, I will be left with half L by L C. So, if it is smaller, I will be left with this, but if it is longer than L C, let us see what will happen. Just erase this out. If it is longer than this, now what is this is sigma fu. So, what is the average stress? It is a trapezium. So, sigma fu into L is the total L, So, this plus this we will have to sigma fu and multiplied by this plus this divided by 2. So, this is L plus this is L plus L minus L C, L minus L C. So, this is this distance is L minus L C, this is L minus L C, this divided by 2, that is the stress. Average stress will be divided by So, this is the stress. So, this is the area of this triangle, divided by L will give us the average stress, and this divided by sigma Fu will give us the efficiency factor. So, this will cancel out. So, what I am left with twice L minus L c divided by twice L. So, which will give me 1 minus L c divided by 2L, L c divided by 2L. So, that is the length efficiency factor, and that is what we have seen earlier in the previous slide. We have seen that 1 minus L c divided by 2L if L is greater than L c. So, if L is greater than L c, we see that it is 1 minus L c divided by 2L, it is 1 minus L c divided by 2L. All right. So, here we are efficiency factor, length efficiency factor, but the orientation efficiency factor have been suggested by people. It is equals to 1 for a line and 1/3 to 3/8 for 2D random in plane, right, because it can be spreaded in all 3 directions. So, 1/3 and 1/6 or 1/5 for 3D random, right. So, 1/6 or 1/5 for 3D random, because there are 6 directions. So, orientation factors based on simple statistics plus experimental work. So, this has been arrived at. So, next we will look into critical fiber volume, and that is defined as a fiber volume required to enhance the tensile strength of the matrix. For example, if we put few pieces of fiber in a matrix, stray pieces of fiber in a matrix 1 or 2, they will not be able to bridge the crack, because crack simply may pass in between. So, I need a minimum volume of fiber that will ensure that cracks are bridged by the fiber. I need some minimum quantity of fiber. When I have sufficient quantity of fiber, at least some fiber will be bridging the crack, some fiber will be bridging the crack. So, right now, to understand that, we will have to look into we will have to look into what is the what is how L c is related. L c is the critical length, that is what we said, and L c is actually related to sigma Fu r by tau. How? Let us just see, because the stress from the fiber to the matrix is transferred through bond. So, if tau is the bond strength, so L c by 2 through which sigma Fu is developed. So, sigma Fu pi r square, that is the stress onto the fiber. I am talking only of one fiber, is good enough for my purpose at the moment. One fiber, single piece of fiber in case of aligned fiber. So, this is the force into the fiber, and that must be transferred through the length of L c, through the length of L c by 2 through bond. So, if the bond strength is tau, twice pi r is the surface perimeter multiplied by L c by 2, that is the area through which actually the bond stress is transferred, bond is transferred into the bond strength tau. So, tau multiplied by this one must be equals to sigma Fu by pi r square. So, this should give us L c equals to sigma Fu r by tau. So, if you want to find out now the length efficiency factor for a aligned fiber, you got to know the bar diameter, you got to know the bond strength, bond stress that can develop into sigma Fu as a strength in the strength of the fiber, ultimate strength of the fiber. So, L c can be calculated in this manner, and we can now look into critical fiber volume, which is required in order to have strength enhancement. So, just consider this diagram. This fiber volume varies from 0 to 1, and I plot between strength and fiber volume. Now, you can easily understand that when fiber volume is 0, this is nothing but sigma mu, this is sigma mu, this will be sigma mu, right. Now, when I have some fiber volume, so I will have actually sigma, this line sigma mu, it is sigma mu is when the fiber volume, because we said that sigma composite is equals to V m sigma m plus V f sigma f. So, I can write this as V m 1 minus V f, because I am plotting against fiber volume fraction actually. You can see it varies from 0 to 1. So, as I go on increasing the fiber volume, V m can be written as 1 minus V f. So, what I will write sigma m u into 1 minus V f at failure, because if the fiber is stronger, well, let me just again tell you this. I am talking of the situation where fiber is stronger than the matrix. There can be a situation where fiber is weaker than the matrix, then of course, strength will reduce down sigma mu, and you will have a reduction in strength. It will have a reduction in strength, but most of the time we use a fiber which will have strength higher than the fiber, because you are replacing part of the material. This relationship still remains valid, that sigma composite is equals to V m sigma m plus V f sigma f. So, if this V f is equals to 0, it is simply sigma mu into, and then V becomes 1 straight away. But supposing my fiber is weak, then what will happen? This will actually be lower value, this will reduce down the strength. So, as I go on increasing the fiber, you are replacing a stronger material by a weaker material. So, actually strength will reduce down, but normally we use fiber which is stronger, therefore, strength will get enhanced. Now, this sigma m can be written as V m can be written as 1 minus V f into sigma m plus V f sigma f. So, you can see it is a linear. Now, supposing the matrix fails earlier, so this will be sigma mu, matrix fails earlier, it will be sigma mu, and this will sigma f will be equals to, actually sigma f will be equals to epsilon at failure epsilon mu into E of the fiber, because the matrix fiber will not fail, the stress in the strain in the fiber on the matrix is same, as long as so the load carrying capacity when matrix is just failing will increase in this manner in a form of a straight line, all right, in the form of a straight line. So, that is what it is. So, therefore, sigma f V f sigma m 1 minus V f, that is the line, and if it is ultimate, then it will be sigma mu. Now, as I increase the fiber, strength will increase. Now, just look at the simply fiber, this is for the fiber, sigma fu V f, sigma fu is the ultimate load carrying capacity or ultimate strength of the fiber into V f. So, that would increase in this manner when you have 100. So, this corresponds to actually sigma fu, this will corresponds to sigma fu, as we shall see, because 100%, and as depending upon. So, this is the contribution of the fiber, this is the contribution of the fiber which will increase, maximum contribution of the fiber, this is the maximum contribution of the fiber, and will increase as I increase my volume fraction. Now, this could, I can write this as sigma mu V f, if this is sigma mu failure, and I can write this as sigma mu V f. Now, as my fiber content increases, a time comes when fiber alone can take the load even if the matrix fail. So, that would require this much fiber content. So, this we call as V crit. What is V crit? V crit is the fiber content. At that fiber content, even after matrix has failed, strength will be enhanced. So, critical fiber content is that strength, content is that strength which or that fiber content at which or beyond which, at and beyond which, even after the matrix fails, the fiber will, this should be sigma mu actually, sigma mu. This at even after which even after that, when matrix fails, the fiber will be able to carry that load, right. So, matrix cracking, once matrix cracks, the fiber should be able to carry the load, but it does not matter. We will see that some cases it does not, many cases it is not, because V critical can be very such large that you may not be able to add them. There are practical difficulties of workability. So, you may not be able to add that, we will see that later on. But even if you do not add, still you get certain properties enhancement, okay? We will see that. So, but the critical fiber content will be defined like this, it is the E of the composite, modulus of elasticity of the composite into epsilon mu ultimate strain in the matrix divided by sigma fu. So, because at this point sigma fu V f must be equals to the must be equals to the strength of the composite, which is actually the strain is C epsilon Fu and modulus of elasticity of the composite is epsilon EC. So, this EC so we create epsilon mu. Now, epsilon mu EC can be written as, you can show that as EC can be, this can be written as EC is nothing but E of the fiber into E of the fiber into Vf plus E of the matrix into 1 minus Vf. So, you can write it in this manner, and epsilon mu can be multiplied here, all of them, epsilon mu and epsilon mu. Now, this gives you sigma mu. So, sigma mu. So, you will get a relationship of this kind, E c in this part, you will get, just I am writing this, it will be E f V f into epsilon mu plus sigma mu minus sigma mu into V f, So, if I take sigma, if I take out V f common from this, so I will get a relationship, of sigma mu minus sigma mu minus. So, all this will be, has to be divided by sigma Fu. So, if I separate this, I can if I write it, I mean, I think I will do it in this manner, maybe I have a slide next. So, what I am trying to do is, I have got E c epsilon mu, and this I am trying to write as E f V f epsilon mu plus E m epsilon mu into 1 minus V f. So, this I will get as E f V f epsilon mu, right, plus sigma m u into 1 minus V f. So, if I take V f common, I will get sigma mu out plus E f epsilon mu minus sigma mu into V f. So, that is what it would be, and if I divide this by sigma f u, if I divide this by sigma f u, now sigma f can be again related, actually sigma f can be related to sigma f u E f. So, V f crit will be this divided by epsilon mu. So, sigma mu, sigma f u epsilon mu, just let me just see this one, what did I write. So, this is this portion E c into epsilon mu will be given by this. Now, this divided by sigma f u. So, sigma mu divided by this plus epsilon E f epsilon mu minus sigma f u. So, I am trying to get an expression for V f. If I am trying to get an expression, this divided by sigma f u should be is equals to. So, this is everything is, I am trying to get an expression for V f. This must be equals to sigma f u V f crit. This must be equals to sigma f u V f crit, sigma f u V f crit, because E c this E c epsilon mu divided by sigma f u was equals to V f crit. So, therefore, if I write V f crit, so this will be also Vf crit, this will be also this will be also, so it will be expression was epsilon c epsilon mu divided by sigma fu is equals to Vf crit. Now, this can be expressed in terms of Vf crit, and that is what I did. And so, what I write is f sigma fu Vf crit is equals to Ec was, what was Ec? Ec was sigma f sigma Ec I wrote as sigma f multiplied by, what did I do actually, just a minute, let me erase this out. So, Ec I wrote as composite was composite E was E of the f Vf epsilon mu plus Em epsilon mu into 1 minus Vf. Now, this will be now Vf crit, and if you write this expression Vf crit, you can get on the left hand side, which will have, this is nothing but sigma mu. So, Vf crit will be written as epsilon, this Vf crit, if I just derive it fully, sigma fu Vf crit is equals to Ef Vf crit epsilon mu plus sigma mu minus sigma mu into Vf crit. So, only term which does not have Vf crit is this. So, therefore, Vf, this I take Vf crit common, Vf crit common here, and from common from this term. So, I will get sigma f Vf crit will be equals to sigma mu divided by sigma fu, this term, minus Ef minus Ef epsilon mu, Ef epsilon mu, and then this minus sigma mu, So, sigma fu, so that is what was my expression, that is what my expression was, sigma mu divided by sigma fu, because sigma fu comes, Vf crit come on this side and Vf crit come on this side also. So, if you take all the terms on the left hand side, then you will get only one term which is actually sigma mu, that is Em into epsilon mu, this will remain here, and Vf crit you can get an expression of this kind. So, you get an expression of Vf crit along in this manner, because we express Ec is equals to E of the fiber into Vf plus E of the matrix into 1 minus Vf. So, this you just change this and put here Vf crit, the Vf crit terms will go to the left hand side here, it is sigma fu Vf crit, and only term that will be remaining is Em multiplied by epsilon mu, which is sigma mu, and this expression will result. So, this is the amount of fiber you require to have strength enhancement. Now, you see it is dependent on sigma mu, sigma fu, and of course, the modulus of elasticity of the fiber. So, more the modulus of elasticity of the fiber, you will require, these terms become smaller. So, you will require more, and so on and so forth. So, one can see this is a function of all those, right. So, Vf crit one can estimate in this manner, right, but it is quite difficult in some fibers to add actually Vf critical fiber. So, because of workability, and therefore, strength enhancement you may not get, but if you get it, well and good. It will depend upon, of course, the L by D ratio and many other factors which we will look into. But let us see what happens when you have a strong fiber and weak matrix. So, this is my matrix and these are my fibers, right, and I am applying pull along this direction, and let us say again it is all aligned. So, as I apply my pull, it will, matrix is failing first, because I have said my matrix is weak. So, weak matrix, it will fail first, and therefore, cracks will come at certain regular spacing, In fact, at this point in the crack, there is some slippage also. Fiber will take all the load, because it is still strong, it can take all the load, fiber will take all the load, and therefore, it will take additional stresses, We will come to this additional stress later on. We can understand this additional stress will be the stress that was carried by matrix. So, matrix was carrying actually sigma mu into V m. Now, this must be the additional stress in the fiber, and that must be equals to delta sigma f into V f, because volume fraction of the fiber. So, this is the volume fraction of the fiber quantity is still remaining same, that must be equals to. So, additional stress can be simply found out as sigma mu V m divided by V f, that will be the additional stress. So, you will have uniformly distributed crack and not a one single crack, and uniformly spaced cracks, and that is actually good. Uniformly spaced cracks, they would be separated almost by uniform distance as long as it is aligned as we are seeing. While if you have even short random fiber, then also you will have crack spacing aligned, crack spacing at uniformly distributed large number of cracks rather than one brittle local failure with brittle failure. So, you will have large number of cracks, they will not allow failure to occur in one go, in sudden failure will be avoided. That is what that makes it ductile, right. That is why it makes it ductile, pseudo ductile we call it. So, load from fiber is transferred. Now, if you look at the crack scenario, load at this point, it is the fiber which is taking the load. From this point, load is transferred to the from the fiber to the matrix, and of course, again in this point it is 0. So, here load is transferred from matrix to the fiber. Earlier we said that just at the end of it is transferring from matrix to fiber, here from fiber to the matrix, because here fiber is carrying everything, fiber is carrying all the load. So, load from fiber is transferred to the matrix, that is crack to the center, from crack to the matrix, from crack to the center, Now, on an average number of fiber I can think of number of fiber n, I can just write like this V f divided by pi r square. If it is aligned, we are talking of aligned scenario. So, V f divided by pi r square, volume fraction divided by pi r square, that will be the number of fiber, actually pi r square into L. So, L is same, L is length is same. So, it will be simply this should be written as L into area, and this also would be so it will be same pi r square into. So, number of fiber will be written, average number of fiber will be like this. So, therefore, single fiber, how much is the crack spacing we want to find out, because the load is transferred from crack, this is my crack, to the fiber, and maximum stress that can attain in the matrix is sigma mu into V m. Maximum stress that would be attained in the center will be sigma mu V m, and again it is 0. So, this is transferred through x 2 x dash, if I call this as 2 x dash. If this distance is 2 x dash, right, or x dash. So, if I call this as x dash, so it will be transferred through x dash. If whole distance is 2 x dash, so it will be transferred through x dash. So, x dash into twice pi r, where r is the radius of the. So, this is the parameter into x dash into tau is a bond stress multiplied by number of fiber that is there per unit volume. So, and this or your total volume. So, unit volume fraction of this is the fiber volume fraction x into sigma mu, that would give me an expression for x dash, that is your crack spacing. So, it will give me an expression for crack spacing. So, x dash therefore, so one can write V m sigma mu twice pi r x dash tau, n can be replaced simply V f by pi r square, and this will result in a simple expression for x dash, because r cancels out with this, pi cancels out with this. So, I am left with twice tau V f, and I am interested in x dash is remaining. So, V m sigma mu, and the r here will come here, r comes here, V f comes here, twice tau comes here. So, that is your my crack spacing, half crack spacing. Crack spacing will be twice x dash, right. So, crack spacing will be twice x dash. The strain would actually vary in this manner. How? Here the strain, matrix strain is 0, this is strain, matrix strain is 0, then it reaches to a at the center sigma mu or epsilon mu. At here it reaches epsilon mu, and then again it comes back to 0. So, actually now the fibers will be additionally strained or stressed. Additionally stressed, we have seen the additional stress, which was actually we said was delta sigma F was equals to sigma mu V m divided by E f. So, that is what we said was the additional stress that will be taking into account additional stress. So, this is the additional stress that would be taken by the fiber, therefore, correspondingly there will be additional strain in the system. So, fiber take more strain, and strain here the perfect the bond through the bond stress has been transferred to the matrix, and they are perfectly bonded here, and therefore, here it will be epsilon mu in both of them, right, because their strain is same in the fiber and the matrix. So, that will be same, and again this will reduce down, strain in the fiber will increase. So, we would like to find out what is the additional strain in the system if you are interested in finding out this x dash, because x dash is there, but find out the what is the w, that is the crack width, increase in crack, how much is the crack, increase in the crack width. If you are interested in finding out that, then we will find out. So, this what is happening, let us understand this. So, from here the strain is increased. So, the epsilon mu is here. Originally fiber was matrix was strained up to this throughout, now this strain, this amount of strain, or this strains have all gone to the fiber. It was matrix was equally strained epsilon mu just before failure. Now, this strain has gone to the fiber. Now, this strain has gone to the fiber. So, fiber is additionally stressed, and eventually fiber was also before failure, everything was at epsilon mu. So, all fiber as well as matrix and matrix both were at epsilon mu. Now, this changes occur. Right. Now, let us find out. So, due to crack and increase in apparent strain, overall strain will also increase. And there is a total elongation will have occurred in the composite. And that would include the crack width. Also. So, apparent increase in the strain would be observed. Now, let us see how it is. Increase in the strain at the point of matrix cracking, let us see. Sigma mu V m divided by V f is the stress, right. Sigma mu V m divided by V m is the additional stress the fiber is taking. See, this term we have already seen, that is actually this divided by E f is the additional strain at that point. So, additional strain at this point, if you look at this is the crack and this is another crack, and we said. So, this additional strain it is taking delta epsilon c, this will be its maximum here and 0 there. Earlier everybody was taking epsilon mu. Now, this height would be average strain increase would be half of this. So, this height will be bearing this V m sigma mu divided by V f divided by E f. So, this height will be simply V m sigma mu divided by V f divided by E f, because this was the additional stress. So, this will be the additional strain here, Now, half of this is the average increase in strain in the fiber, So, delta epsilon c is the average strain increase in the fiber. Earlier it was epsilon mu, right, average strain increase in the fiber, all right. So, this is what it is. So, if you write this f sigma mu, write it as epsilon mu into E m, then you can write it as alpha, where alpha is defined as this, So, this what we are talking of additional strain in the actually composite will be, because everything was at epsilon mu earlier. Now, this is the additional increase. So, everything was at epsilon mu earlier. This strain we have found out, and half of this, because it goes from 0 to this height. So, half of this average would be simply given by this, and that is how we are finding out. So, this gives you alpha, where alpha is defined like E m by E f, V m by V f. So, that is the increase. Therefore, originally the strain was this is the average increase in the strain, average increase in the like crack width I am trying to find out. So, this is the strain increase into 2 x dash alpha epsilon mu by 2, that is the average increase in the strain, and plus epsilon mu was the equal strain everywhere, but there is a minus epsilon mu by 2 as well, because the matrix has reduced. Matrix strain is now not epsilon mu, actually it is the total strain would be this epsilon mu plus as much as is there. So, but matrix has, there is a reduction in the matrix. So, the total earlier the stress in all cases were same. So, earlier stress in all cases were same. So, half, this is the increase, this is the additional strain being taken by the there is a composite, there is an increase in the additional strain, average increase in the strain, and this minus this crack width. If I am interested, I should be actually finding out this is the additional average increase in the strain minus the matrix has actually, there is a reduction in the matrix strain. Now, average strain in the matrix is half epsilon mu by 2, half epsilon mu by 2. So, matrix strain now is half epsilon mu by 2, average strain in the matrix is half epsilon mu by 2, originally it was epsilon mu. So, this multiplied by the length 2 x dash over which it has actually occurred would give you it will give me the So, if I bring in 2, I will get it 1 plus alpha epsilon mu. So, this is simple algebra, this 2 will cancel out. So, that is the strain, and this diagram shows you that actually, this diagram shows you that, this diagram shows. So, this was alpha epsilon mu, and this height, that increase is epsilon mu 1 plus alpha, but average will be average increase. So, this is 1 plus alpha, that is what we have seen, and average increase will be alpha, half of this. It was 1 plus alpha, it was 1 plus alpha. So, average, if I am trying to find out the crack width, I can find out by multiplying the length of this one. So, this is the crack width at failure. Sigma fu of course is equals to, now after that it is the matrix which will take the strain alone, and it will be at failure finally sigma fu, sigma composite, Cu composite will be sigma fu into Vf, and that is what is shown. That is what is shown in the previous diagram that we have seen. At failure it will be sigma fu, this is sigma fu into Vf, that would be the sigma Vf at ultimate failure would occur if it is failing anywhere alone. So, if it is failing alone, and then it will be sigma fu Vf finally at failure, sigma fu Vf at failure, right. So, sigma fu strain at failure, of course, one can find out what will be the strain at failure, because strain at failure will be the less than the, this diagram will make it clear. This diagram, strain at failure will be less by sigma fu, failure would have been here, but it would be less by some amount. So, if I look at the stress strain diagram, what I will see, up to this nothing fails, it is epsilon mu, then there is a sudden increase of alpha epsilon mu by 2 because of the crack. So, apparent increase, sort of a ductility provided by this, and after that it will be Ef Vf curve which would follow, and finally will fail at sigma fu Vf. So, this will be sigma fu Vf, it will fail at sigma fu Vf. So, the strain is somewhat less than epsilon fu, strain at failure is somewhat less than sigma fu. By how much? By geometry you can find it out actually from here to here, this length. So, it will be epsilon fu minus 1 plus alpha, this increase that has occurred, 1 plus alpha, 1 plus alpha epsilon mu. So, epsilon mu 1 plus alpha 2 plus 1 plus alpha 2 is here, that is because after the crack has formed, this is the strain, and this is strain plus sigma fu minus this is the additional increase between this point sigma fu minus 1 minus alpha epsilon mu. So, this total gives us actually epsilon fu alpha by 2 epsilon mu. So, epsilon this gives us. So, this is what this is the strain after the crack has formed, that is what we have seen. Then sigma fu bf minus EC epsilon mu divided by EF BF, that is from the similar triangle that I was talking about, and you get it epsilon mu 1 plus alpha by 2, and if you divide by EF by BF. So, this will be alpha epsilon fu, because EF divided by sigma fu, and EC by EF sigma mu by epsilon mu by BF. So, EC by epsilon mu by EF BF, this term will be simply EM BM plus EF BF into epsilon mu, replacing EC by this, and this will again give you 1 plus alpha epsilon mu. So, therefore, these two terms put together, I get the strain at failure, and it comes out to be epsilon fu minus alpha by 2 into epsilon mu, because this length is same as this length, or this is if it would have gone here, but now it has gone here, that is basically because of this length change. So, it is related to that, and from that we have derived from the similarity of triangle, this relationship has been derived from the similarity of triangle, this relation epsilon fu bf sigma fu bf minus EC epsilon mu, that is the stress in the matrix. So, from the similar triangle divided by EF BF, this relationship has been derived, and you will have strain at the failure as this. Anyway, that is still fiber. So, now supposing I take practical fiber concrete, we barely can put in critical fiber. So, this portion we do not get. What we normally get is something of this kind, depending upon your fiber, some A or B type, say steel fiber concrete, percentage of fiber will vary, and I can have a small amount of enhancement. So, with this actually you can look into crack spacing in short fiber, crack spacing in long fiber we can find out, crack spacing in long fiber we can find out. Now, crack spacing in short fiber we can derive from this, crack spacing in short fiber we can derive from this, all right. So, I think this is what we will look in the next class, continue with this short fiber. But one more thing I would just like to mention here is that most of the time short fibers do not fail by failure of the fiber, snapping of fiber rarely occurs. So, it is essentially the pull out of the fiber which actually causes failure of the fiber. So, short fiber, first we will look into what will be the crack spacing, but then we will look into the force required for pull out, 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 and then force required for pull out, and lastly then how this, although I may not be able to get an enhanced enhanced strength, tensile strength, still I may be able to get enhanced flexural strength. So, we will look into that in the next class, in our next lecture. Thank you very much.